Hello my dear students. So I am going to continue the lesson rate of reactions, and in the previous chapter we discussed some factors that affect the rate of reaction. So you all know there are 4 factors. What are they? The surface area of reactants, the temperature, the concentration of reactants and catalyst. In the last chapter, I ended the chapter by explaining how the concentration of reactants increase the rate of reaction. When the concentration increases, the rate of reaction increases. So you can remember the example also. We observed the rate of reaction in regard to magnesium reacting with hydrochloric acid. So there we change the concentration of hydrochloric acid. We observe the rate of fizzing. So when the concentration increased, the rate of fizzing increased. So from that we were able to conclude that the rate of reaction increases when the concentration increases. So there, when we said concentration, the reactant was a solution, hydrochloric acid solution. And also you can remember students, we used equal sizes of magnesium string. So the amount of magnesium did not change, but the concentration of hydrochloric acid was different. There I mentioned to you all, when the reactants are in the gaseous state, then of course, instead of concentration, we consider the pressure of gaseous reactants. So this is again similar to concentration. Concentration for solutions, and if it's the reactants are in the gaseous state, then we consider their pressure. Now this diagram is given to you in your textbook, students. There is a mistake. Now here you can see this is a high volume, larger volume. This is a smaller volume, but the labels have to be switched. When the volume is high, the pressure is low. So here this should be low pressure condition and this should be high pressure condition. I will explain that to you all first. So can you all remember an activity that we did in one of your previous grades? Are you all familiar with compressibility of gases? I am sure you know that. By applying a force, if you can decrease the volume of a substance, then that is known as compressibility. And you all know gases can be compressed. To do that, what did we do? We took a piston. Like this, we take a piston and we have air in it, right? What you can do is, you can place a finger there. You can touch the opening of the piston with your finger and then you can push this piston inwards. So when you push the piston inwards, what do? You decrease the volume. You decrease the volume. When you decrease the volume, what do you feel on your fingertip? You can feel the increasing pressure. And you can push the piston to a certain point and thereafter you cannot push it further. You cannot bring it closer to this point. You can't completely compress the air. You can compress it to a certain extent. There you will decrease the volume and you can feel the pressure increasing. So you have to remember, students, for a fixed amount of gas, for a fixed amount of gas, when volume decreases, the pressure increases. So if we want to have a fixed amount of gas, what we can do is, we can take a closed container. So into a closed container, if it is closed, nothing can come in, nothing can go out. So air cannot come in or air cannot go out. That means the gas that is inside a closed container is a fixed amount of gas. But if you can decrease the volume of that container, you can increase the pressure. If you increase the volume, you can decrease the pressure. So this pressure will also affect the rate of reaction. This is how that happens. Now, like I said before, you have a closed container. Now, inside this, you have, let's say, reactants, 3 particles. Let's say reactants A and B. The same reactants are there inside a small volume. Now, here you can see volume less, pressure high. Here volume more, so pressure less, but the same number of particles. You can see 3 blue color particles and 3 pink color particles. The same here. So if there are 2 reactants in the gaseous state, then of course you can see when the volume decreases, the pressure increases. And you can see here, since this is a small space. Now you all know gas particles, they always involve in random movement. They are free particles, there is very less interaction between the molecules or the particles of gases, and therefore they move randomly. And when they are supposed to move randomly within a small volume, what will happen to the number of collisions? There will be more collisions here. There will be less collisions there. So volume is more, pressure is less. There is less number of collisions in a unit time, but here there will be more number of collisions in a unit time. Because of that, the rate of reaction will be greater. So in this, you can see, students. Now volume is less, pressure is high. There is more collision. So rate of reaction is greater. Here, of course, there will be less collisions compared to the previous one. So rate of reaction is less. Can you think of an example for this one? We have discussed this with balancing equations. Nitrogen gas reacting with hydrogen gas forming ammonia gas. If you balance this reaction, you need to have a 2 there and 3 there. So 1 nitrogen with 3 hydrogen giving rise to 2 ammonia molecules. So here, if you increase the pressure, then rate of reaction will increase. Is that clear to you? So this is again similar to concentration, but for reactants that are in the gaseous state. So nitrogen is a gas, hydrogen is a gas. Here the product is also a gas. So the important thing is the reactants are gases. Then you increase the pressure by decreasing their volume. When you increase the pressure, the number of collisions per unit time increases. Therefore, the rate of reaction increases. So that is what you need to understand. Now if we go back to the slide, can you see this now? I told you all to correct this diagram, the labels given under the diagram in your textbook. This should be low pressure condition, this should be high pressure condition. So there. Pressure of gaseous reactants. When gaseous reactants are involved, the rate of reaction can be increased by increasing the pressure. Very important. Here, rate of reaction can be increased by increasing the pressure. Consider the instances A and B illustrated in the figure given below. So, this is what I told you all to correct. Figure A and B. There are two reactants here. We will take the red particles as one reactant and the blue particles as another reactant. If you count the particles, there are 4 red particles and 4 blue particles. The same number in B also. 1, 2, 3, 4, 1, 2, 3, 4. So, there are 4 red and blue particles there. So, 2 reactants, the same amount of reactant particles. But you can see here the volume is less, here the volume is more. So, because of that, here the pressure is high. In the first one, the pressure is low. So, what will happen there? There will be less number of collisions between particles here. There will be more number of collisions between the particles in instance B. Because of that, the rate of reaction is high at instance B. So, if we read the explanation, masses of reactants in the case of A and B are the same. So, here we say masses. When we say masses, we counted the number of particles. There are 4 particles of red and 4 particles of blue color reactants. So, that means the same mass of both the reactants in both instances. But the pressure of the reactants in B is higher than that of A. So, like I corrected it to you all, you can see here. The pressure of the reactants in B is higher than that of A. That is very important, as the volume of B is reduced. So, when you decrease the volume, pressure increases. Then the rate of reaction in B is higher than that of A, because the number of collisions of reactants per unit time is higher in B. Is that clear to you all? So, because the number of collisions of reactants per unit time is higher in B. This is what I explained to you. So, you all know the effect of concentration of rate of reaction. When the concentration of reactants increases, the rate of reaction increases. The same thing if the reactants are gaseous reactants. If the reactants are in the gaseous state. I gave you all an example. The nitrogen and hydrogen both are gaseous reactants. They react to form ammonia. In that particular reaction, the reactants are gaseous reactants. So, there, if you increase the pressure by decreasing the volume, you can increase the rate of reaction. Why? Because when you decrease the volume, the number of collisions per unit time increases. So, because of that, the rate of reaction increases. You have to remember that, student. So, with that, I will move on to the next slide. So, then the last factor. We have already discussed the first 3 factors: surface area of reactants, temperature and concentration. The last factor is catalyst. Now, what is a catalyst? It is also a chemical substance that increases the rate of reaction without being chemically consumed during the reaction. It does participate. It somehow increases the rate of reaction. It can undergo some physical changes, but it is not chemically consumed. I will explain that. Before that, I will write what a catalyst is. A chemical substance that increases the rate of a reaction without being chemically consumed is known as a catalyst. So, if we look at an example, students, what is this? H2O2, that is hydrogen peroxide. Hydrogen peroxide. Can you all remember the reaction? When we prepared oxygen, to collect oxygen gas in the laboratory, we can use hydrogen peroxide. What happens there? When you heat hydrogen peroxide, we got water and evolving of oxygen gas. So, to balance that, we can put a 2 there and 2 there. So, the reaction is balanced. For this reaction, you can remember, we heat this solution in order to quickly collect the oxygen gas, in order to increase the rate of reaction. In the previous lesson, when we wanted to collect oxygen, we said we can heat the hydrogen peroxide. If we don't want to do that, or if we want another method to increase the rate of reaction, what we can do is, we can add manganese dioxide, MnO2. MnO2 is manganese dioxide. Now, if you add a small amount of a very little amount of manganese dioxide to a test tube containing hydrogen peroxide, you will see the rate of fizzing, that is rate of evolving of oxygen gas, will be higher. That means the rate of reaction will be high. So, this effect of manganese dioxide is to increase the rate of reaction. So, we said it is a chemical substance. So, manganese dioxide is a chemical substance or just a substance that increases the rate of reaction. So, that is, it increases the rate of this reaction, increases the rate of evolving of oxygen without being chemically consumed. What is that? Now, say, if you take, let's say, a beaker, into that you take hydrogen peroxide, and into this, if you take 0.2 grams of manganese dioxide. So, before the reaction, you take the manganese dioxide, you weigh it accurately, you put it into hydrogen peroxide, you allow the reaction to take place. And once the reaction is complete, you filter this solution. So, here, after the reaction is complete, then filter the solution, and what you can do is collect MnO2, dry it and weigh it. You will have the exact same 0.2 grams of manganese dioxide. Maybe if you took it as a large cube of manganese dioxide, it would have become powdery. The nature would have changed, but the mass of manganese dioxide will remain the same. If you took 0.2 grams, at the end also you will have 0.2 grams. So that means the manganese dioxide, the catalyst that you took before, is still there. So it has not been chemically consumed. That is the meaning of that. Does not chemically consume during the reaction, or it is not chemically consumed during the reaction. So when we look at what catalyst is, a chemical substance that increases the rate of reaction without being chemically consumed is known as a catalyst. catalyst. So you have to remember that. To understand the effect of this catalyst, we will do an activity now. Activity. Let us find out the effect of catalyst on the rate of chemical reaction. So the same reaction that I explained to you all before. So these are the materials that we need. We need test tubes and we need hydrogen peroxide, and we need manganese dioxide. Manganese dioxide, I gave you all the chemical formula, MnO2, and hydrogen peroxide, H2O2. So this is what we will be doing. You take equal sizes of test tubes, you measure equal volumes of hydrogen peroxide, but into one test tube, you weigh a certain amount of manganese dioxide. You take it into one test tube and then you pour the hydrogen peroxide solutions, equal volumes, into both the test tubes. And you observe what happens there. You will be observing the rate of fizzing and there you will see the change. That is a simple activity. We look at the procedure again and then we will do the activity. So the method. You all can see here, students. Add equal volumes, that's important, equal volumes of fresh hydrogen peroxide solution. Now this is important, students. Why do we need to take fresh hydrogen peroxide? Now hydrogen peroxide, even if you don't provide heat or if you don't have a catalyst, the reaction takes place slowly. Now hydrogen peroxide can be decomposed into water and oxygen even at room temperature. The reaction is very slow, but still that will happen. So if you have an old solution of hydrogen peroxide, we really don't know whether it's hydrogen peroxide or whether it has been converted to water and oxygen. So that is the reason why you need to take fresh hydrogen peroxide. So it's only hydrogen peroxide. So add equal volumes of fresh hydrogen peroxide solutions into the two test tubes. Tip: accurately weigh. So accurately weigh. Again, to observe that the catalyst is not chemically consumed during the reaction. Accurately weighed 0.2 grams of manganese dioxide into one of the test tubes. Observe the speed of evolution of gas bubbles from the above test tube. So 2H2O2 aqueous giving rise to 2H2O liquid and oxygen gas. When the reaction is over, filter the solution with manganese dioxide, dry the residue and weigh it. This is also important. When you, after filtering it, you have to dry the residue before weighing it. What is the reason? Now we are going to check whether we have the same amount of manganese dioxide. If it is not dry, you will get the weight of water as well. So before weighing it for the second time, that is after the reaction, you have to make sure that the manganese dioxide is completely dry. Then you can see you will get the same mass of manganese dioxide. If you took 0.2 grams, you will have 0.2 grams after the reaction is complete. Then you can confirm that it is not chemically consumed during the reaction. So that is again a simple activity, students. I'm sure you all have understood the procedure. Let's go to the lab and do the activity now. Okay, students. So now we are going to do this activity in order to observe how the catalyst affects the rate of reaction. So what is a catalyst? A chemical substance that increases the rate of reaction without being consumed during the reaction. So here as the catalyst, we will be using manganese dioxide. So here you can see, students, it is a black color powder manganese dioxide. That is the catalyst. So this is going to catalyze the decomposition of hydrogen peroxide. You all can remember the reaction, students, when hydrogen peroxide H2O2 is decomposed or undergoes chemical decomposition, it turns into water and liberates oxygen gas. So that is the reaction that we are going to observe now. So I have hydrogen peroxide here. I will be using equal volumes of hydrogen peroxide. So that is the same amount of reactants, only the catalyst will be different. So into one test tube I will add this catalyst, into the other test tube I will not be adding the catalyst. So to confirm that the catalyst is not consumed during the chemical reaction, what we need to do is we need to weigh the mass of the catalyst initially. So here I have already weighed 0.2 grams of manganese dioxide. So this is 0.2 grams of manganese dioxide. And once the reaction is complete also, we will have to filter it, dry it and weigh it again to confirm that you have the same amount of catalyst remaining after the reaction. Start the reaction. What I will do is I will measure 10 milliliters of hydrogen peroxide and that will be taken into two test tubes. Two test tubes both containing 10 milliliters of hydrogen peroxide each. So here I have taken 10 milliliters of hydrogen peroxide. I will transfer that into one test tube. The same way, another 10 milliliters. So another 10 milliliters of hydrogen peroxide. So I will transfer that into the second test tube. So now here, students, we have the both the test tubes with equal amounts of hydrogen peroxide, 10 milliliters each, and into one test tube I will add this 0.2 grams of manganese dioxide. So I'll add it into this. Observe what happens. So if you observe now, can you see the fizzing there? That is because hydrogen peroxide is being decomposed into water and oxygen. You are observing the liberation of oxygen gas. You can see the very fast fizzing. You can see the very fast fizzing, students. In this test tube where we have manganese dioxide, it catalyzes the reaction and it occurs fast. If you look at this one where there is no manganese dioxide, you can see at the bottom there is a little amount of fizzing. Just a few gas bubbles can be observed. That's because hydrogen peroxide is getting decomposed, but when you compare the rate of reactions, this is very fast. So from that, you can understand manganese dioxide increases the rate of decomposition of hydrogen peroxide to water and oxygen. So that means manganese dioxide is a catalyst. Can you all observe this clearly? Here also at the bottom, if you look at it, you can see a very few gas bubbles. So that is how the reaction takes place. We need to wait till the reaction is complete. So here still the reaction is occurring. When I mix it also, you can see it clearly. The reaction is very fast. So while I wait for the reaction to complete, I will get this ready. Now here you can see, students, I have already set it up. The funnel in the stand, it has been kept on the stand, and also the beaker is set here. So I will place the filter paper here, and when the reaction completes, we can filter this solution. Still you can see, students, the reaction is taking place. So we will have to wait for some more time. But at the same time, if you compare it with this one, can you all see any change here? Here also the reaction will be taking place, but very, very slowly. So if you have hydrogen peroxide for a very long period of time, it will decompose into water and oxygen, but the reaction takes place very slowly. But with the catalyst, it is a fast reaction. Still, we need to wait for some more time. So students, now that the reaction is complete, we will filter the solution. So here I will transfer it into this filter paper. When we put a small amount of the solution, it will get filtered. So in order to transfer this manganese dioxide that is remaining here, I will use some water and I will wash it off into the funnel. So I will wash this amount of manganese dioxide also. We will So I have washed all the manganese dioxide, everything has been transferred, almost everything. But here you can see a slight amount remains on the test tube, but that cannot be avoided. These are the practical errors, students. So I have transferred it. Here you can see the drop wise it is getting filtered. If we touch the surface of the beaker, then of course you can see the water getting filtered as a stream. So there the filtration process is somewhat faster. We will have to wait for some time until everything is filtered. Then of course students, we will have to dry the magnesium dioxide. So it has to be completely dry and then we will have to weigh it again. So if you weigh it again, you will be able to observe that there is almost 0.2 grams of manganese dioxide. So that is how the catalyst acts. We took 0.2 grams of manganese dioxide. It participates in the reaction. That is how it increases the rate of reaction, but it is not chemically consumed during the reaction. That is why we are able to get the same mass of manganese dioxide after the reaction is complete. But it has to be completely dry before we weigh it. So I am not going to do that activity. You all have to remember we should filter it, we should dry it completely and then we weigh the mass of manganese dioxide. So the catalyst, when it increases the rate of reaction and does not get consumed in the reaction, the physical state might change. That is the property of catalyst. So from this observation, we saw when we put manganese dioxide into hydrogen peroxide, the rate of fizzing was very fast. Still you can see we don't see much fizzing here. It's almost like a clear solution. So from that you can understand the activity of a catalyst, and catalyst always increases the rate of reaction. Okay students. So did you all observe the activity carefully? You all were able to see that the rate of fizzing in the test tube containing only hydrogen peroxide was very slow, almost like there was no rate of fizzing at all. But you observe that when we had manganese dioxide in the second test tube, the rate of fizzing was fast and the reaction went to completion also very quickly. So you were able to see that. So in the presence of manganese dioxide, the rate of reaction of the decomposition of hydrogen peroxide to water and oxygen, the rate of reaction was increased. But when there was no catalyst, the rate of reaction was slow. So from that, you can confirm and say manganese dioxide increases the rate of reaction. That means catalyst increase the rate of reaction. So there was another part to the activity. We were supposed to filter the solution and dry the manganese dioxide substance, solid residue, and then we were supposed to weigh it. But I did not do that part in the lab. So you can remember that. But I explained to you. It has to be very, very dry. Then only you need to weigh it. Then you will get the same mass of manganese dioxide. From that you can understand that it is not chemically consumed during the reaction. That is a catalyst. So the observation, rate of fizzing is high in the test tube with manganese dioxide. So that was the observation. Rate of fizzing is high in the test tube contained with manganese dioxide compared to the test tube without manganese dioxide. Compared to the test tube without manganese dioxide. So from that we can conclude and say manganese dioxide that is MnO2 is the catalyst and catalyst increase the rate of reaction, and also catalyst is not chemically consumed during a chemical reaction. So manganese dioxide is the catalyst. Catalyst increase the rate of reaction and the catalyst is not chemically consumed during a chemical reaction. So those are the observations and conclusions that we got from the activity. So there you all can understand the function of a catalyst. With that students, I'll move on to the next slide. Okay. So here again, if I write the reaction for you all. Now we had hydrogen peroxide, H2O2, aqueous. From that we get water, that is a liquid, and oxygen, that is a gas. So to balance the equation, we need to have 2 hydrogen peroxide giving rise to 2 H2O and 1 oxygen. For this reaction, we used manganese dioxide, that is MnO2, as the catalyst. So that is the important component here. Catalyst increase the rate of this particular reaction. The speed of evolution of gas bubbles is higher in the test tube with manganese dioxide. Manganese dioxide has increased the rate of this reaction. Since the mass of manganese dioxide remains the same, it has not been consumed during the reaction. That is, manganese dioxide has acted as a catalyst for this reaction. That is very important. So you can have a reaction that can take place at room temperature very slowly. If you heat it, there also the rate of reaction will increase. At the same time, if you add a catalyst, then also the rate of reaction will increase. So you have to remember, students, Catalyst is a substance that increases the rate of reaction without being chemically consumed during the reaction. Now, similar to catalyst, there are substances that can reduce the rate of reaction. Then we call them as inhibitors. Inhibitors. Now here, it is a substance that increases the rate of reaction. This increases the rate of reaction. Rate of reaction. So that is a catalyst. Catalyst. But inhibitors decrease the rate of reaction. Decrease the rate of reaction. So in the next slide, I will explain an example of an inhibitor. The same reaction, the reaction of hydrogen peroxide aqueous giving rise to water liquid and oxygen gas. So balance the reaction. Now for this reaction, if you add manganese dioxide, it is a catalyst. It increases the rate of reaction. To the same reaction, if you add sulfuric acid, H2SO4, here the rate of reaction will be decreased. Rate of reaction decreases. So that means the sulfuric acid is an inhibitor. In addition to the substances that speed up reactions, there are substances that reduce the rate of reactions. These are known as inhibitors. Very important. Substances that reduce the rate of reaction are known as inhibitors. Example, a few drops of sulfuric acid can be used to reduce the rate of dissociation of hydrogen peroxide. So the same reaction is also called as dissociation of hydrogen peroxide. Decomposition or dissociation, because it divides into two other products. Dissociation or decomposition of hydrogen peroxide. Usually decomposition is when we heat the reaction. Here we don't heat it. We either add the catalyst or we either use an inhibitor. Catalyst increases the rate of reaction. Inhibitors decrease the rate of reactions. So if we compare the three, now you can have 3 test tubes with equal volumes of H2O2 and that also H2O2. Here we can take manganese dioxide. Here we can put few drops of H2SO4. If I label them as 1, 2 and 3. Now what can you say about the rate of reaction? Rate of reaction two is just a hydrogen peroxide solution. So it will slowly react. But for 3, we have added a few drops of sulfuric acid. So it inhibits the reaction, reduces the rate of reaction. So the reaction becomes slower. Whereas here, in the first one, we have added manganese dioxide. That is a catalyst. So there, the rate of reaction will be faster. So if you arrange them in order of rate of reaction, 3 will be the slowest, then 2 will be a little bit more faster, 1 will have the fastest rate of fizzing or the fastest rate of reaction. Why? We have a catalyst here, we have an inhibitor there. So that is how we use catalyst and inhibitors. So here catalyst, here this is an inhibitor. So these catalysts and inhibitors are used in our day-to-day life. Even inside our body as well as in day-to-day life, we use these substances. So mainly the catalyst. So we will discuss some examples where we use catalyst or we come across catalyst in our day-to-day life. With that, students, I'll move on to the next slide. So before we look at the uses, we will try to understand the characteristics of a catalyst. We have discussed it before also, but again, to understand the characteristics of a catalyst, small amount is enough for a large amount of substrate. So even for a very large amount of substrate, a very small amount of the catalyst is enough. If you remember, in the previous reaction, we just used 0.2 grams of manganese dioxide. That is a very small amount. So small amount. For example, we used 0.2 grams of manganese dioxide. So that was enough to speed up the rate of reaction of dissociation of hydrogen peroxide. And they are specific for each reaction. Now for hydrogen peroxide, we use manganese dioxide as the catalyst. But you cannot use a different catalyst to speed up the reaction of hydrogen peroxide. So when we say specific, manganese dioxide is a catalyst that can speed up the reaction of dissociation of hydrogen peroxide. You cannot use the same catalyst for a different reaction, or you cannot use any catalyst for all the reactions. That is what we mean by they are specific for each reaction. So small amount is enough and they are specific. So that means for the reaction of dissociation of H2O2 aqueous, manganese dioxide is the catalyst, which gives rise to water and oxygen gas. So this is specific. Manganese dioxide is a specific catalyst for this particular reaction. Like this, we will be discussing some more catalysts. Again, they are also specific. For example, if we want to produce ammonia, I explained that reaction to you all, nitrogen and hydrogen react to form ammonia. For that reaction, porous iron is used as a catalyst. Now for that reaction, if you use manganese dioxide, nothing will happen. The same way, if you put porous iron here, that will not change the reaction of hydrogen. It will not act as a catalyst there. So like that, the catalysts are specific to reactions. And the third one, that is also something that we have discussed before, its chemical composition does not change during the reaction. That is what we said as it is not chemically consumed during the reaction. You take 0.2 grams, the same 0.2 grams will remain after the reaction. But there can be physical changes. That's important. There can be physical changes. So like I said, if you take a chunk of the particular catalyst, it can become powdery because the reaction is taking place inside a liquid medium, solution medium. So because of that, the physical nature can change. It can be changed physically, but it is not chemically consumed. So three properties that you need to remember. Small amount is enough for the catalyst to increase the rate of reaction. It is specific to different reactions. And also, they are not chemically consumed, or the chemical properties don't change, but there can be physical changes. This is what you need to remember as characteristics of catalyst. Is that clear to you all, students? So with that, we'll move on to the next slide. So here, as I told you all, there are some chemical industries that use catalysts. Now this table is given in your textbook as well. So in this column, you have the chemical industry. Now for example, Haber process of manufacturing ammonia. I told you all this. I have shown you all the reaction also. Haber process of ammonia, there nitrogen gas reacts with hydrogen gas, giving rise to ammonia gas. So to do that, we balance the reaction. You can remember we discussed pressure. When pressure increases, the rate of reaction increases. The same way, we can use a catalyst to increase the rate of reaction. And this process, where nitrogen and hydrogen react to form ammonia, is known as Haber process. Name of the manufacturing process, Haber process. And in this, they use porous iron as the catalyst. Porous iron. Porous iron. Now, when we say porous, there are small spaces, holes. Now, iron, you all know, is a metal and it is a solid substance. There, the iron atoms are completely, neatly arranged. But here, when we say porous iron, there are spaces between, very tiny spaces, very tiny pores in iron. That increases the surface area of the catalyst. You have learned this before when we discussed nanotechnology in a previous grade. So you can remember that also. So porous iron, it has tiny pores, tiny spaces through which the substance, the gaseous reactants can go into those pores. And there, the iron can act as a catalyst. That's why we use porous iron. Then the next one is contact method of manufacturing sulfuric acid. Another name. The name of the process is contact method. You know what sulfuric acid is. H2SO4. Here also there is sulfur dioxide that is converted to sulfur trioxide. Then it is reacted with water to form sulfuric acid. There is oxidation and all those different reactions take place. In that, vanadium pentoxide. The catalyst known as vanadium pentoxide. Vanadium pentoxide. That is the catalyst used in this process. Contact method of manufacturing sulfuric acid, H2SO4. Then we have the third one, manufacturing nitric acid by oxidizing ammonia. The ammonia can be oxidized, reacted with oxygen and nitric acid. You know the chemical formula, HNO3. Nitric acid can be produced. In this process, we use platinum as the catalyst. The third type of industrial process. Then the last one, manufacturing margarine by hydrogenation of unsaturated fats. Now, can you all remember what unsaturated fats are? If we take organic compounds, the fats, lipids, there are fatty acids, saturated and unsaturated. When we say unsaturated, there can be either double bonds between carbon or there can be triple bonds between carbon. These are unsaturated substances. We have discussed this in your first lesson when we discussed biomolecules. Under lipids, we have fats and oils. Oils are made up of unsaturated fatty acids. Fats are made up of saturated fatty acids. If it is a saturated compound, there will be only single bonds for all the carbons. So, this is saturated. You can remember that. I'm sure you all can recall that also. So, if there are unsaturated compounds, they can undergo hydrogenation. This is also something that we have discussed before, students, when we discuss the uses of hydrogen. Now, you have an unsaturated compound like that, carbon, where it's something like this. To this one, you can add hydrogen. That is known as hydrogenation. So, this becomes a saturated compound. Hydrogens get added. The other two bonds still remain. There are two bonds for each carbon. There is a double bond. To one of the double bonds, hydrogens are added and it becomes a single bond. So, this becomes a saturated compound. Now, for this also, we use a catalyst. and the catalyst is nickel. Nickel, again a metal. So that is also a catalyst. Manufacturing margarine by hydrogenation of unsaturated fats. For that we can use nickel. So can you all see that, student? Haber process of manufacturing ammonia, we use porous iron. Contact method of manufacturing sulfuric acid, we use vanadium pentoxide. When manufacturing nitric acid by oxidizing ammonia, we use platinum. And manufacturing margarine by hydrogenation of unsaturated fats, we use nickel. So there also you can see different processes, different catalysts. So the catalyst is specific for the reaction. Can you all understand that? So here I have just shown you all additional information, the reaction of nitrogen and hydrogen to form ammonia, then what unsaturated and saturated compounds are, and also when an unsaturated compound gets hydrogenated, it becomes a saturated compound. This occurs during the manufacture of margarine. For that, we use nickel as the catalyst. So I am sure students, you all were able to get more information about catalyst. There are few more information that you need to know. I will discuss that in the next slide. So this is again for extra knowledge. Enzymes necessary for biochemical reactions. We have discussed this before. Biochemical reactions in organisms like respiration, digestion, photosynthesis and protein synthesis. So you know what respiration is. Glucose is oxidized with oxygen to produce energy. You can remember that takes place in the mitochondrion of the cell. So cellular respiration. Then digestion. You eat complex food, it gets digested and the nutrients are absorbed by the body. So during that digestion process, there are many chemical reactions taking place. Then photosynthesis, you remember that also. Carbon dioxide and water in the presence of sunlight or light energy inside chlorophyll. You need to have chlorophyll. So there glucose is produced and oxygen is produced as the byproduct. So there are many chemical reactions. Then protein synthesis. Protein synthesis takes place in ribosomes of the cell. So these are all reactions related to organisms. That is why they are biochemical reactions. And all these biochemical reactions are catalyzed by enzymes. So enzymes necessary for biochemical reactions in organisms like respiration, digestion, photosynthesis and protein synthesis are also biological catalysts. So we saw catalysts, they were chemical substances. If you have enzymes, those are biochemical catalysts or biological catalysts, which increase the rate of biochemical reactions. So biological catalysts are known as enzymes. We have discussed enzymes before also. You can remember they are all proteins. All the enzymes are proteins. Can you remember an example? Again, the first lesson. The action of or the activity of amylase. For example, salivary amylase. We have discussed that. What does this do? It hydrolyzes starch to maltose. It actually, when we say hydrolyzes, there is starch. Starch is hydrolyzed to maltose. And this particular reaction is, the rate is increased by salivary amylase, or it is catalyzed by salivary amylase. So you can remember all these. This is the hydrolysis of starch to maltose. Inside your mouth, starch gets hydrolyzed to maltose. We did an activity also. You can recall that. So that enzyme is a biological catalyst, and they are all proteins. So like this, there are many other enzymes. Lipase is there, thioline is salivary amylase, then there is amylase inside the intestine, there is maltase, there is sucrase, pepsin, renin, trypsin, like that. There are so many different enzymes related to our digestive system. We will discuss all those functions in your next grade. So for now, you all need to know that the biological catalysts are enzymes. And these enzymes increase the rate of many biochemical reactions like respiration, digestion, photosynthesis, and protein synthesis. In addition to that, these biochemical reactions, there are some synthetic biological catalysts, and they are used as detergents. Now, these biological catalysts are used as detergents. How does that happen? Now, say if you have a piece of cloth, and in that, if there is a stain, say when you are eating some food, the food spills on your dress and there is a stain. And if the stain is either a fat or a protein, then like I said here, to hydrolyze lipids, fat is a lipid. So there is the enzyme lipase. Then if this enzyme is there in the detergent, that will remove the fat stain. Like that protein, for different types of proteins, there are different enzymes. Commonly, they are known as proteases. Protease. So these enzymes remove the protein stain. So if it's a lipase, it can remove a stain created by a lipid. Protease is an enzyme that acts on protein. Then that will remove the protein stain. So like that, there are many different types of enzymes. You can notice something, students. Now, amylase, ACE, lipase, ACE, protease, ACE. Like that I said, sucrase, invertase, maltase. The names of all these enzymes end with the suffix ase. So, if you see that, you can immediately identify it as an enzyme, a biological catalyst. So, that also increases the rate of reaction, but here it is a biochemical reaction. Is that clear, student? So, with that, we will move on to the next slide. That is again for extra knowledge. Catalytic converters. Now, this is something where we use catalyst in motor vehicles. Catalytic converters. Catalytic converters. In modern motor vehicles, there is a part fitted to the exhaust system. Now, you all know through the exhaust only, when there is ignition of fuel, the combustion is taking place, gases are being released, and those gases are given out through the exhaust. And to this exhaust system, they connect a part which is called the catalytic converter. Now, this catalytic converter actually converts some of the poisonous substances, poisonous gases that are present in the exhaust. Its function is the conversion of pollutant gases like carbon monoxide and nitric oxide into non-pollutant gases. So, what are pollutant and non-pollutant gases? A gas, if it is there in the environment, if it can harm the environment, if it can harm the people, if it can harm the animals, plants, if it has a toxic property, poisonous property, then it becomes a pollutant. So, these pollutant gases, for example, carbon monoxide, it's very toxic to us also. It can bind with the hemoglobin in our blood, and that can become very poisonous, very harmful to us. It can sometimes become fatal also. So, to that extent, carbon monoxide is a toxic gas. So, because of that, that has to be converted to a different form. Same goes for nitric oxide. So those are pollutant gases. They are converted to non-pollutant gases. Catalysts in these converters increase the rate of following reactions. So as an extra knowledge, you should know these reactions, students. 2 carbon monoxide gas. CO gas is carbon monoxide. With oxygen becomes carbon dioxide. Now carbon dioxide you know is a greenhouse gas, but compared to carbon monoxide, it is not toxic because we do have carbon dioxide in the environment. So that is not toxic. So this is a pollutant gas, this is a non-pollutant gas. So that is why the reaction. The catalytic converter, the enzymes or the catalyst actually convert carbon monoxide to carbon dioxide. Here nitrogen monoxide, NO. Nitrogen oxide, NO, again 2 NO gas plus 2 CO gas gives rise to N2 gas and CO2 gas. Again, all these gases are there in the atmosphere, nitrogen and carbon dioxide. So these are non-pollutant gases. These two are pollutants. When you say pollutants, they are usually toxic or poisonous. Poisonous gases. So those are the catalysts that facilitate or increase the rate of these reactions. As an extra knowledge, you all have to remember that, student. Is that clear to you all? So with that, I will move on to the next slide. There is an assignment. Study the catalyst used in various chemical industries and chemical processes as well as the biological catalyst. So chemical industries and the biological catalyst or enzymes involved in biochemical reactions. Prepare a booklet using the information collected. Libraries as well as printed and electronic media can be used for this purpose. So I have introduced what biological catalyst enzymes are, and also we looked at some industrial catalysts used in industries. You can remember porous iron, then there was vanadium pentoxide, then there was nickel, then there was platinum, you can remember. Now porous iron for the Haber process of manufacture of ammonia. Then vanadium pentoxide for the contact process of manufacturing sulfuric acid. Then nickel for the hydrogenation process in manufacture of margarine. And platinum was used as the catalyst in the production of nitric acid by oxidizing ammonia. So different catalysts used in different chemical industries. Then we looked at biological converters or catalytic converters. Then biological catalysts used in detergents. Then also I gave you all some examples for enzymes. Now enzymes I told you all salivary amylase that we have discussed before. Then I mentioned to you all the lipase with detergents, then protease. In addition to that, I told you all, I mentioned maltase, sucrase, then pepsin, trypsin, rennin. All these are different types of catalysts. So all those are there. You can get information from libraries, from printed materials, and also from the internet. So you collect information, their property, to what specific reaction they act as the catalyst, and how they are useful. Like that, you can collect some information and make a small booklet where you mention about the catalyst and the reaction they catalyze. So then you will have more information. So this is something that you need to do. I have just summarized what we discussed before. All the catalyst and enzyme that we discussed in the previous slide. So with that, students, I have actually come to the end of this lesson. In the next slide, I will discuss the summary. So, we discuss the rate of reaction and the factors that affect the rate of reaction. So, with that, I'll move on to the summary of the reaction. Summary. Various chemical reactions occur at various speeds. So, we saw a lot of very slow reactions. Some take days, weeks, months, years, and there are very fast reactions which we have seen in the lab. So, they occur at various speeds. Rate of a reaction is the amount of change taking place in a unit time. This is very important. This is the definition for rate of reaction. Rate of reaction is the amount of change taking place in a unit time. Either the rate at which the reactants are consumed or the rate at which the products are formed. So, factors affecting the rate of reactions are surface area of reactants or the physical nature. That is where we discuss the solid substance and powder substance, calcium carbonate. When it is powder, the rate of reaction is high with hydrochloric acid. So, surface area of reactants. Then temperature at which the reaction occurs. So, for that only we looked at the example where we put an iron nail into acidified potassium permanganate and we observe the rate of or time taken for decolorization. When the temperature is high, the time taken for the decolorization process is less. So, we know when temperature increases, the rate of reaction increases. Then the next one, concentration of reactants. For that, we looked at the reaction of magnesium with hydrochloric acid. You take more hydrochloric acid, more concentration, then the rate of reaction is high. And in all these, you were able to understand when these factors are increased, the number of collisions in a unit time. The number of collisions between the reactants in a unit time increases. That is why the rate of reaction increases. So, this concentration is for solution or liquid reactants, mainly solution. But pressure is considered for gaseous reactions. So, that also I have explained to you. And catalyst. So, catalysts are specific to reactions. They increase the rate of reaction and they are not chemically consumed. But there are substances that decrease the rate of reaction also. What are they? The inhibitors. So, knowledge of rate of reaction is widely applied in chemical industries and chemical processes. So, those are the examples we saw in the previous slides. Industrial processes where we use catalyst. And about the biological catalyst, those are the enzymes in detergents, in catalytic converters. So, those are all different applications. And knowledge of rate of reactions is important for day-to-day activities also. So, when we say day-to-day activities, sometimes we increase the temperature in order to increase the rate of reaction. Say when cooking, sometimes we increase the temperature to cook faster or to carry out certain processes. Now, certain food has to be cooked at higher temperature. Certain food is cooked at lower temperature. There are also chemical reactions taking place. Then we decrease temperature. Now, say we keep food in the refrigerator, so that we reduce the temperature and we prevent food spoilage. So, there by changing the temperature, by increasing, we increase the rate of reaction. If we want to stop or reduce the rate of reaction, we decrease the temperature. So, because we have knowledge related to rate of reactions, we are able to apply that in our day-to-day life. Same goes for the applications of catalyst. From that knowledge only, we get many advantages. So, this again is a small topic. I am sure you all would have understood all these concepts that were discussed, and I am sure you have a very good understanding. So, with that, students, I will end this chapter, and in the next chapter, I will discuss the questions given in your textbook. So, like I always tell you all try the questions first and then you can listen to my discussion.